Now, in this video, we are going to take up one more problem on thermal stresses. So, to do that, first we are going to read the problem. Problem number 61. A steel tube of 50 mm outer diameter and 10 mm thick is fitted into the copper tube of ID 50 mm and 10 mm thick. They are connected by using 20 mm diameter pin at its ends as shown in this figure. This figure it says here, this is the pin what you have. You have a steel tube of 50 mm OD, that is steel tube of 50 mm OD, this cross section, and 10 mm thick. So naturally is fitted 10 mm thick means this is the 10 mm thick what you have, that is the steel tube. They are fitted into the copper tube of ID. Copper tube ID is 50 mm, so this is the copper tube. The outer one is the copper tube, and 10 mm thick, so you're going to get 60 mm. And 10 mm on either side, so OD will going to become 70, and this is 50, OD is 50, and 10 mm thick means minus 20, so that will going to become 30 mm ID. If the length of the compound bar is 600 mm, so the length of this is the compound bar is 600 mm, find the stresses produced in the tubes and pins when the temperature is raised by 25 degrees centigrade. Given the coefficient of thermal expansion of steel, which is 12 into 10 to the power of minus 6 per degree centigrade, and coefficient of thermal expansion of copper is 17.5 into 10 to the power of minus 6 per degree centigrade, and Young's modulus of steel is 2 into 10 to the power of 5 Newton per mm square, and Young's modulus of copper is 1.2 into 10 to the power of 5 Newton per mm square. So this is the problem which is given. So now we're going to try to solve this problem. So to do that, first we're going to have the temperature which is 25 degrees centigrade. So area of copper we want to have, that is pi by 4 into outer diameter minus inner diameter. So pi by 4 into 70 square minus 50 square. So on simplification of this, you're going to get it as 1884.956 mm square. Similarly, area of steel tube, pi by 4 into 50 square minus 30 square. So that will going to give you 1256.637 mm square. So then, as the free expansion of copper is more than the expansion of steel, so naturally the copper will be under compression, or the compressive stress will going to be developed in the copper, and tensile stress is developed on the steel. So keep it in the same position. So to do that, for equilibrium, what is that? PS plus PS is equal to PC. So what is PS? PS is nothing but load on the steel. So naturally PS will be equal to sigma S into AS, that will be equal to sigma C into AC. So then you have the area of copper and area of steel. Substitute the values of AF and AC, which is sigma S into 1256.637, that will be equal to 1000 sigma C into 1884.956. So on simplification, sigma S will be 1.5 times sigma C. So you are going to get this. Next, what we know is delta S plus delta C, that is the deformation in the steel bar plus deformation in the copper bar, which is equal to. So here the coefficient of thermal expansion of steel is alpha S into T into L minus alpha C into T into L minus alpha S into T into Ls. That is basically because free expansion of steel, so alpha S into T into L. So then we will going to have the Ls is equal to Lc, that is equal to L, which is 600. So as we know, PS into L by AS into ES, delta S plus delta C will be equal to PC into L by AC into EC. So that will be equal to alpha C minus alpha S into T into L, which is the common factor. So you take out the L there. So sigma S by ES plus sigma C by EC, that will be equal to alpha C minus alpha S into T. So because LL it gets cancels. So then we are going to have, you know that sigma S is equal to 1.5 times sigma C. So 1.5 times sigma C plus divided by Young's modulus of steel, which is 2 into 10 to the power of 5 plus sigma C divided by 1.2 into 10 to the power of minus 6, and alpha C, coefficient of thermal expansion of copper, is 17.5. Substitute those values, 17.5 into 10 to the power of minus 6 minus 12 into 10 to the power of minus 6, which is the coefficient of thermal expansion of steel, multiplied by the whole thing is multiplied by 25, that is the temperature change. So then we are going to get in the LCM form, take out the LCM, that is 2 into 10 to the power of 5 into 1.5, 1.2 into 10 to the power of 5 in the denominator. So that is multiplied by 1.5 into 2 into 10 to the power of minus 5. So that will be, it should be 1.2 into 10 to the power of minus 5 into sigma c. So here 1.2 gets cancelled, sigma c into 2 into 10 to the power of 5, which will be equal to, so 1.375 into 10 to the power of minus 4. So you are just simplifying those things, simplifying the values. So you're going to get the sigma c value, stress induced in the copper tube, which is sigma c, which will be equal to 8.684 Newton per mm square, because it is under compression, because the coefficient of thermal is more. So naturally the copper tube will going to have the more expansion than the steel tube. So now the stress induced in the copper tube will be sigma s is equal to 1.5 times sigma c. So that will be equal to 1.5 into 8.684. So you substitute the value of sigma c here, and then on calculation you will go to get it as 13.026 Newton per mm square. So again it will be a tensile stress. What is the stress induced in the pins? So the stress induced in the pin is tau p, which will be equal to P by 2 into AP, because they have two sides you have. So naturally area of pin and P is the load which is coming on the pin. So to do that, what is P? Sigma S into AS or sigma C into AC by 2 into AP. So what is that? Sigma S is 13.026. So sigma S is 13.026 into area of steel into 1256.637 divided by 2 into area of pin is pi by 4 into 20 square. So pi d square by 4. So the value of this will be 26.052 Newton per mm square. So it will going to be the shear stress. So this is how you will be able to calculate the stresses and also the stresses developed in the pin. Thank you.